Welcome to your IELTS listening practice from Spinta.org. This is a mini-test designed to help you practice a specific section of the exam and improve your confidence. The recording will be played one time only, just like in the official test. Let's begin.
Good afternoon, everyone. Today, we will explore the fascinating world of quantum computing with a specific focus on its fundamental principles of superposition and entanglement in information processing. Quantum computing represents a paradigm shift in the field of computer science. Unlike classical computers, which rely on bits as the fundamental unit of information, quantum computers utilize qubits. A qubit can exist not only in a state of 0 or 1, but in a variety of states through the principle of superposition. To understand this, let's first define what a bit is. In classical computing, a bit can be either a 0 or a 1. This binary system is sufficient for most computing tasks. However, the limitation becomes apparent as we look to complex problems that require more computational power. In contrast, a qubit can represent 0, 1, or both simultaneously due to superposition. This means that a quantum computer can process a multitude of possibilities at once. Thus, rather than information being stored in discrete bits, in quantum computing, the information is stored in continuous qubit states. Now, let's delve deeper into superposition. When we discuss superposition, we refer to the ability of quantum systems to exist in multiple states at the same time. Rather than saying a qubit is simply either 1 or 0, we can say that it exists as a combination of both, which is expressed mathematically by complex probability amplitudes. It's important to understand this concept of superposition because it leads directly into our next key principle, entanglement. When we have 2 or more qubits, they can become entangled. This phenomenon occurs when the state of one qubit becomes dependent on the state of another, no matter the distance between them. For example, if we have 2 entangled qubits, measuring the state of one qubit instantly gives us information about the other qubit's state. This relationship is not subject to classical limitations, suggesting that information might be transmitted instantaneously despite distance, which challenges classical concepts of information processing. Additionally, entanglement plays a crucial role in quantum computing applications, particularly in quantum communication. Thus, meaningful and secure quantum communication could be achieved since the entangled pairs will always remain correlated. A real-world example that exemplifies quantum entanglement and its application is quantum key distribution, or QKD. In this process, 2 parties can share a secret key securely, using entangled particles. Any eavesdropping would disturb the entangled pair and thus reveal the presence of the intruder, ensuring the security of the communication. To put it into context, the unique characteristics of qubits in superposition allows one quantum algorithm, known as Grover's algorithm, to search through unsorted databases quadratically faster than any classical computer. This illustrates the power of quantum computation enabled by these principles. On the other hand, while superposition allows numerous computations to be performed simultaneously, entanglement creates correlations that facilitate solving complex problems more efficiently. When combined, these 2 quantum phenomena allow quantum computers to vastly outperform classical computers in certain tasks. Fascinatingly, the application of quantum computing extends beyond just theoretical physics. For instance, in chemistry, quantum computers can more accurately simulate molecular interactions than classical computers can, dramatically advancing drug discovery methods and material science. Furthermore, the implications of quantum computing in cryptography are profound. Conventional encryption techniques rely on classical algorithms that can be rendered insecure by the capabilities of quantum machines. Quantum computing could potentially break many of the cryptographic systems currently in place if security measures are not updated to adapt to this new landscape. In addition to its applications in cryptography and communication, quantum computing may have benefits in optimization problems, which are commonly encountered in logistics and supply chain management. By harnessing entanglement and superposition, These challenges can be addressed in ways that were previously unimaginable with classical computing. Now, let's summarize the critical roles of superposition and entanglement in quantum information processing. First, superposition offers vastly increased computational capacity by allowing qubits to represent multiple states simultaneously. Second, entanglement provides correlations that enable high-speed data transfer and complex computation by connecting qubits regardless of distance. In conclusion, the principles of superposition and entanglement are foundational to the operation of quantum computers. They provide a framework that deviates from traditional computing methods, highlighting the potential of quantum technology. As quantum computing continues to evolve, the implications of these principles will likely reshape numerous fields, leading to advancements we are only beginning to comprehend in the realms of both science and technology. Thank you for your attention today, and I am now open to any questions you might have regarding quantum computing or the principles we discussed.
You have now completed the practice test. When you are ready for a full exam experience, visit us at Spinta.org. There you will find complete mock tests for all 4 skills: listening, reading, writing, and speaking. Our platform provides instant AI feedback for your speaking and writing tasks, along with an accurate prediction of your band score. Take control of your preparation at Spinta.org.